Welcome back to CSConnect series. We are in data representation. This video will be on alphanumeric codes. System handles numerical data as well as non-numerical data. It means it handles not only numbers but also letters of the alphabet. As a human, I can understand ABCD are letters of the English language. For system, everything has to be represented in form of binary codes. The combination of numbers as well as alphabets is called as alphanumeric. The binary code for alphanumeric characters is called as alphanumeric code because it contains the code for both the alphabets as well as numbers and few other characters too. What does this alphanumeric code consist of? It consists of the 10 decimal digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It consists of the 26 alphabets A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z and special characters like comma, full stop, blank. So far in the binary codes that we have seen, whatever we saw in BCD, XS3, gray code, 2421 weighted code, everything had only 4-bit combination because it represented only 0 to 9 digits. But here we are including alphabets and some special characters. Just count the digits and alphabets alone. It is 10 plus 26 which will give you 36. Along with 36 you have at least one special character. So the count of characters that are involved here will be greater than 36. 10 from digits, 26 from alphabets and few from special characters. The total number of elements involved in this will be greater than 36. When you want to represent 2421, you needed a 4-bit code. When you represented 8421 for 0 to 9, you needed a 4-bit code. Till 15 also it is applicable. 2 power 4 is just 16. What about 2 power 5? It is 32. But there are more than 36 characters. That's why we say 2 power 5 which is equal to 32 is insufficient for storing this alphanumeric code. Then how many bits are we going to consider? We will take a minimum of 6 bits of code. 2 power 6 is 64. It is greater than 36 and alphanumeric code must be at least 6 bits so that you can represent all the characters. So the first code that we are going to see here is internal code. Alphanumeric characters are internally used for data processing. And these internal codes are not used for transmission purposes. It is more convenient to use a 6-bit code to represent 64 characters. How did we get the 64 characters? 2 power 6 is equal to 64. This 6-bit code will represent 26 uppercase letters of the alphabet, numerals 0 to 9 and up to 28 special characters. 26 plus 10 will give 36. 36 plus 28 will give 64. So they have given up to 28 special characters it can support because of 64 characters. This set of characters is usually sufficient for data processing purposes. That is why it is called as internal code. Why are they specifically saying this much character is sufficient for this purpose? It is because using fewer bits to code characters has the advantage of reducing the memory space needed to store large quantities of alphanumeric data. Most computers translate the input code into an internal 6-bit code. So this is an internal representation strictly for data processing and not for transmission purpose. Let's see how the internal codes are there. Each character is assigned a decimal number. One code is of 6-bit length. 0 to 63 can be represented in this way. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. So all together 6 bits. What are the representations converted as? 2 power 5 is 32, 2 power 4 is 16, 2 power 3 is 8, 2 power 2 is 4, 2 power 1 is 2, 2 power 0 is 1. The first set of character will be the digits 0 to 9. I already said every character is assigned a decimal number. Why is a decimal number associated with every character? The 6-bit code is based on this particular decimal number. If this is going to be the digit of the character, this will be the decimal number. In the internal code representation, 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6 is 6, 7 is 7, 8 is 8 and 9 is 9. There is no change. So how do we write 1? We will put zeros here and only 1 will be present here. 0 means it will have all zeros here. 2 is represented here, 3 is represented this way, 4 is represented this way, 5 is 101, 6 is 110, 7 is 111, 8 is 1000, 9 is 1001. The remaining places will all have 0. This is how these codes are created. 0 to 9 is not a very big issue. Let's get into the alphabets now. We have to represent them now. 17 is 16 plus 1. So these two places will have 1. 18 means 16 plus 2. 19 means 16 plus 2 plus 1. 20 is 16 plus 4. 21 is 16 plus 4 plus 1. 22 is 16 plus 4 plus 2. 23 is 16 plus 4 plus 2 plus 1. 24 is 16 and 8. 25 is 16, 8 and 1. After I, we go for J. J is given the number 33. This need not be continuous at all. That's why I have represented the decimal number of every character. 33 means 32 plus 1. 34 is 32 plus 2. 35 is 32 plus 2 plus 1. 36 is 32 plus 4. The remaining places will all have 0. Just to tell you how these representations came, I have collected this decimal number from the code so that we can represent it as a hands-on experience. The next set of characters, N to Z. Actually till 39, 40, 41 it is fine. From 50 it is going till 57. What is 37? 32 plus 5. 38 is 32 plus 6. 39 is 32 plus 7. 40 is 32 plus 8. 41 is 32 plus 8 plus 1. What is 50? 32 plus 16 is 48. 48 plus 2 is 50. What is 51? 48 plus 3 is 51. What is 52? 48 plus 4 is 52. 53 is 48 plus 5. 54 is 48 plus 6. 55 is 48 plus 7. 56 is 48 plus 8. 57 is 48 plus 8 plus 1. The remaining places are zeros. The next set of digits will be the special characters. Where is 32? It is for minus. So here we have 43 and 44. Blank space is 48. And I have taken only few characters. I have not taken all the characters. So 48 can be represented as 1 and 1. 27 means 24 plus 3. So 24, then 3. 60 can be written as 48 plus 12. 60 has only one bit here. 43 is 40, 32 plus 8 and 3. 44 is 40 plus 4. 28 is 16 plus 8 is 24. 24 plus 4 is 28. 32 has only one bit here. 49 has 48 plus 1. 59 has 48 plus 8 is 56. 56 plus 3 is 59. What is 11, 8, 2 and 1? The rest of the places will have zeros. This is actually the internal code representation used by the system. Not for this code but for the upcoming code, you can remember the decimal numbers. Using the decimal numbers, you can find the code easily. The next code that we are going to discuss will be ASCII code. This code is what compilers, programming languages, everywhere it will be used. ASCII code stands for American Standard Code for Information Interchange. Internal code was only used for data processing and not for transmission purpose. When you have the terms information interchange, it means this is used for transmission purpose. This is used to represent more than 64 characters. So we are going to 7-bit code. 2 power 7 is equal to 128. This is the standard code commonly used for the transmission of binary information. For practical purposes, an 8th bit is added for parity, making the 7-bit ASCII code as an 8-bit code. So when you are transmitting something, you have to check whether the code has been received correctly. For that purpose, they are adding this parity. Now 2 power 7 means there are 128 characters totally. So in that, there are 95 graphic symbols. I can say I know A is an alphabet, 1 is a number, 3 is a number, 0 is a number. For system, everything is a symbol. Then we have 23 format effectors. Then we have 10 characters. 95 plus 23 plus 10 will give 128 on the whole. What are the 95 graphic symbols? The first set will be capital A to Z. The second set will be small a to Z. Then we have 0 to 9 numbers. We have certain special symbols and we have punctuation marks. 0 to 9 is represented from 48 to 57 in decimal number, followed by capital A to Z, which is denoted from 65 to 90, followed by small a to Z, taking the value of 97 to 122. When you get into programming, say for example, there will be a expression like is A greater than or equal to B. This is for our eyes. But internally in the system, A is 65, capital B is 66. It will check whether 65 is greater than or equal to 66. And this will throw false as the answer. According to the system, A to Z are not alphabets but are decimal numbers from 65 to 90. So while representing 7-bit ASCII code, capital A is represented as 65. Small z is represented as 122. Previously in the internal code we had only provision for uppercase letters. Here provision is also given for lowercase letters. What are format effectors? They are functional characters for controlling the layout of printing or display devices such as carriage return, line feed, horizontal tabulation and backspace. What about the other 10 characters? They direct the data communication flow and report its status because they are using for transmission purpose. This 10 characters is allocated for data communication flow. Now we will see the ASCII code. So it is a 7-bit code. Altogether we have 7 bits here and the characters will be from 0 to 127. It makes 128 characters. We'll just start with 0 to 9 and then go with blank space and a full stop. How is 48 represented? 32 and 16. 49 is 48 plus 1. 50 is 48 plus 2. 51 is 48 plus 3. This is actually ASCII representation. So definitely you have to know what is the range of decimal values. 52 is 48 plus 4. 53 is 48 plus 5. 54 is 48 plus 6, 55 is 48 plus 7, 56 is 48 plus 8, 57 is 48 plus 9, 32 is only this particular bit is 1, 46, 32 plus 8 is 40, then 44, 46. The remaining places will be 0. 32 is for blank space or just space. This is the full stop or the period. Then the alphabets. It starts from 65. So we are not getting into the small letter, the lowercase characters. We are just doing with the uppercase characters according to the decimal value of the alphabet. And this will have a continuous range, not like the internal code. From 65 it will go continuously till 90. We'll just try to fill up. 64 and 1 is 65. 64 and 2 is 66. 64 and 3 is 67. 64 and 4 is 68, 64 and 5 is 69, 64 and 6 is 70, 64 and 7 is 71, 64 and 8 is 72, 64 and 9 is 73, 64 and 10 is 74, 64 and 11 is 75, 64 and 12 is 76, 64 and 13 is 77, 64 and 14 is 78, 64 and 15 is 79, 64 and 16 is 80. For 81 we have a 1 here. For 82 we are placing in 2. For 83 it is 3. 84 it is 4. 85 it is 5. So 64 and 16 is 80. We are just marking for 6 alone. Here for 7. Here for 8. Here for 9. Here for 10. You can check this at your convenience. So I have added zeros in the remaining spaces. For small a, which is 97, how will we do this? 64 plus 32 is 96 and this is 97. So the remaining places will have zeros. This is how it starts for the lowercase characters. So always remember, capital A to Z is 65 to 90. Small a to Z will be 97 to 122. 0 to 9 will be 48 to 57. The blank space is 32 and the full stop will be 46. At least remember these ASCII decimal numbers. So when there is a need, you can go for coding it automatically with the 2 power 0 set. Next we are going to see about EBCDIC code. What is EBCDIC code? Extended BCD interchange code. This is actually used in IBM equipments. It is nothing wrong to know that these codes existed. They use 8 bits for each character and the 9th bit is added for parity. In ASCII, there were 7 bits and 1 bit was added for parity, making it as 8 bits. In EBCDIC, there are actually 8 bits and the 9th bit is added for parity, making it to be 9 bits altogether. Same character symbols as ASCII, but the bit assignment to characters is different. It means there are different decimal numbers allocated for each character. 8 bits will have 2 power 8, which is equal to 256 characters. Now let's see the 8-bit code character. There are 8 bits totally, ranging from 0 to 255. Now I have taken only few of the alphabets and the numbers along with the full stop here. 193. 128 plus 64 is 192. So this will be 11. 192 plus 1, 192 plus 2, 192 plus 3, 192 plus 4, 192 plus 5, 192 plus 6, 192 plus 7, 192 plus 8. Now we are getting to J, 209. After H we have I and then J. J is having 209. It means it is not continuously allocated here. 192 plus 16 will give 208. 208 plus 1 is 209. Then 226. What is 192 plus 32? It is 224. So we will have 111 along with 2. What is 233? We have 224 then 9. So it will be 8 plus 1 9. 224 plus 9 will give 233. The remaining places can be marked as 0. 0 is actually 240. 192 plus 32 will give 224. 224 plus 16 will give 240. So 192, 32 and 16. All these 4 together will give 240. Then for 241 it is 1 here. 42 it is 2. 43, 44, 45, 46, 47, 48, 49. So we will have 4 ones here continuously. So we have filled up. What is 75? So 64 plus 8 is 72. 72 plus 2 is 74. 74 plus 1 is 75. The remaining places will have 0. So you can have 1 in all these 4 places for 240, and from 1 to 9 you can place 1 in the last 4 columns and then fill the remaining places with 0. For 0 to 9 alone I am saying. There is another code called punch card code. This card consists of 80 columns and 12 rows. You can have a look at the punched card that I got from the web. In the column we have alphanumeric character that is represented by holes punched in the appropriate rows. Regarding the row, the 12 rows are marked starting from the top as 12, 11, 0 to 9 punch. You can divide this punch as two zones. The first three, 12, 11 and 0 are called the zone punch and the remaining 9 are called the numeric punch. The format, how do we actually store? The rows are mentioned and where the hole is punched, giving the ones, will be mentioned. Let's take some example of 12-bit code. A is represented as 12, 1. So the row is mentioned here and where the hole is punched. J is represented as 11, 1. S is represented as 0, 2. And for the full stop, it is 12, 8, 3. So this is a kind of representation. In the earlier days, you may find the 12-bit codes for A to Z, 0 to 9 and also for special characters. The remaining unlisted rows are assumed to be zeros. What is the disadvantage of this particular code? The 12-bit card code is inefficient with respect to the number of bits used because you are using 12 bits there. That's why it is not in use. But you can just at least know that such code existed. Whether it is EBCDIC code or punch card code, we are just knowing it for knowledge purpose. Now we will see all the alphanumeric codes discussed in this video together. So let's take few characters. I am picking numbers from 0 to 4, alphabets from A to F and the space. So 6-bit internal code has the following decimal number and the 6-bit code is represented here. The 7-bit ASCII code 0 to 4 will have 48 to 52, then A to F will have 65 to 70 and blank space is 32. The corresponding code is given and 8-bit EBCDIC code is also given for these numbers and the 12-bit card code from those books are also taken. So for space actually there is no punch. This is just for an overall view. Now we will get into the practice problems of alphanumeric codes. Assign a binary code in some orderly manner to the 52 playing cards. Use the minimum number of bits. So first we have to find how many number of bits we have to allocate to it. In the playing cards you have two things. The first thing is the suit. There are actually 4 suits. We have heart, diamond, club and spade. Heart and diamond will be in red color. Club and spade will be present in the black color. There are numbers from 1 to 10 and after 1 to 10 you will have jack, queen and king. That is J, Q and K. Usually 1 will not be represented as 1. Instead it will be represented by the letter A. So it is A to 10, J, Q, K. If you have played, okay. If you have not played, you can use some solitaire game to at least understand what are the cards present. Now there are 4 suits. How do you represent 4 suits in minimum number of bits? 2 power 2 will give you 4. So you will need 2 bits to represent the suit. So for example, let's take it as 0, 0 for heart, 0, 1 for diamond, 1, 0 for club and 1, 1 for spade. This is just an arbitrary assignment. This is not definite assignment. I am just giving you as an example how to represent it in 2 bits. This is for the suit. So how the cards will be there is, if you take heart, there will be 13 cards. If you take diamond, there will be 13 cards. In clubs, you will have 13 cards and in spade, you will have 13 cards. So in every 13 card, you will have ace to 10, then J, Q, K. These are the 13 cards available. When you add all these 4 cards, you will end up having 52 cards in total. So now we have represented the suits separately. So I will place heart, diamond, club and spade here. So it can be represented as 0, 0, 0, 1, 1, 0 and 1, 1 here. Now let's take the symbol. So A, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, K. And the corresponding number is actually given here. Now we have to find the binary code. So we know 1 is 0001, 2 is 0010. How did we get this code? We have used 8421 code here. So this is 11, 1011, 8 plus 2 plus 1. then 12 is 1100, then 13 is 1101. So if you want to assign these binary codes and see, you can very well do in 8421. Since we have already done it numerous number of times, I have just given you the codes. We know 2 bits are necessary to represent the suit. How many bits are necessary to represent these numbers? 1 to 13 cannot be represented in 3 bits. Till 7, 3 bits is enough. From 8 till 13, you need 4 bits. So in that case, we are going with 2 power 4, which will hold 16 numbers. We are going to have 4 bits. So the minimum number of bits needed is 2 bits for the suit and 4 bits for the symbol or the number given here. So let's take suit and number. So the first 2 bits for the suit and the last 4 bits for the number. Say for example, let's take heart 10. How do we allocate this? Heart is having 0, 0. 10 is having 1, 0, 1, 0. So we will need 6 bits to represent the suit and the symbol together. Let's go for spade 13 or spade K. What is spade? 1, 1 here. So I have simply allocated some numbers. For K, what is the binary code? 1101. So this is how we will be allocating. Assign a binary code in some orderly manner. It is left to our choice. That's why this is taken in our choice. But they have asked us to use the minimum number of bits. So we are taking only 6 bits in total. Now we will go for diamond jack. J, that is 11. So diamond is 0, 1 and J will have 1, 0, 1, 1. Then we will go for club ace. That is 1. So club is 1, 0. A is 000, 1. So this is how we will be representing the cards in binary code. The next problem. Write your first name and last name in an 8-bit code made up of 7 ASCII bits and an even parity bit in the most significant position. Include blank between names and a period after the name. So I have taken the first name as computer and last name as science. In between the names I am including a blank space and after the name I am including a period here. Now let's take the ASCII bits. They are asking add an even parity bit in the most significant position. So what is the most significant position? It is in the starting. Least significant position is after the ASCII code. So we have to add it in front. So let's take the ASCII codes. I have taken the decimal number alone. Let's take computer. What are the values here? 67. 1, 2, 4, 8, 16, 32 and 64. This is 67. What is O? 79. What about M? It is 77. What about P? It is 80. What about U? It is 85. T is 84. E is 69. What is R? It is 82. We have marked for computer. For 32, we know 32 will alone be there. You have 3 ones here. So I am adding another one to make it even. Here there are 5 number of ones. I am adding another one bit to make it 6. Here there are 4 number of ones. So I will add 0. Here there are 2 ones. It is 0. Here there are 4 ones, it is 0. Here there are 3 ones, so I am having 1 here. Here 3 ones are there, so another 1 is added. 3 ones are there, another 1 is added. Only 1 is there, so another 1 is added. Because they are asking us to add even parity bit. Now let's take signs. S is having 83. C is 67. I is 73. For E it is 69. What about N? It is 78. Then again C, you have 1, 4 number of zeros, 1, 1. E is 1, 000, 101. What about the period here? It is 46. Now we have to again write even parity here. 1, 2, 3, 4. 4 ones are there, it is even. C has 3 ones, so we are adding 1. I has 3 ones, we are adding another 1. E has 3 ones, we are adding 1. N has 4 ones, so it is 0. C has 3 ones, it is 1. E has 3 ones, it is 1. So whenever you have odd one, you have to add 1 in parity. When it is even number of 1, you have to add 0 in the parity. So how do you write binary code here? You have to write it as COMPUTER blank SCIENCE full stop. Start with C. You have to include the 8-bit code 1 1 4 zeros 1 1, then 1 1 0 0 1 1 1, then we have 0 1 0 0 1 1 0 1, 0 1 0 1 0 0 0 0. So this is C, this is O, this is M, this is P. You have to continuously write this. Then for U, you have to write 0 1 0 1 0 1 0 1. This is U. For T, 1 1 0 1 0 1 0 0. Just till computer I will write. Then for E, it is 1 1 0 0 1 0 1. Then R, it is 1 1 0 1 0 0 1 0. You have to write computer, then for blank, then for science, then the period. How many characters are there? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 characters are there. So in this 17 characters, one character will have 8 bit. So 17 characters will have 8 into 17 bits, which is equal to a total of 136 bits of zeros and ones will be sent as the binary code. So we are writing the first name and last name in an 8-bit code made up of 7 ASCII bits and even parity bit. With this, we are completing alphanumeric codes topic. I'll meet you in the next video. Thank you, viewers.